those. And if you were here for the last talk, what you heard about was the history of education, higher education in the U.S. And really the last 150, 200 years of education. What I'm going to tell you about is zooming in much more on the present. It's like the mostly last 10 years and a little bit the last 15 to 20 years. But it's really modern history because it's robots and it's surgery and it's the modern technology that we have today. So I want to start by, and the other remark I wanted to make in reference to the previous talk is the structures he talked about in terms of how higher education works with the federal funding of research and just the way that it's set up in terms of faculty having the freedom to study what they want and students coming and working with the faculty to earn Ph.D.s. All of that structure is what's enabled all of the stuff you see here. It's all come from academic labs. Everything I'm going to show today all come from academic labs. It's all started with federal government funding. So all of this stuff, none of it would be possible because all of it was too high risk for companies to tackle. So it's all come from that structure that we just heard about over the last 100 years. And now we're zooming in on what are today's results of that stuff. Okay, so to start, what I want to do is I want to first dispel any myths, or a couple specific ones. And the first is maybe if you came to my talk because of the rise of robots in the operating room, if you're worried about Terminators operating on you, well, that was just a hook to get you guys in here. It's not going to happen. At least not anytime soon, not anytime within any of our lifetimes. We're not going to have these guys cutting us open. Another myth that I want to dispel, which a lot of people have in their, most likely, you either haven't thought about this or you have this picture in your head of sort of the Star Trek operating room. Like, everything that goes on in the operating room is very precise and it's very technological. They wave something over you like a tricorder and it fixes what's wrong with you inside. Or this is what we would wish that it would be, we would hope that it would be, and doctors do nothing to dispel our understanding of the operating room as this. Of course, why would they do anything to dispel it? The fact of the matter is it's very different than this. In fact, this is what a modern operating room looks like. It's a very cluttered environment. There's all kinds of stuff everywhere. There's people doing stuff. The patient's here on the table. The doctor's got the patient cut open, reaching into the patient. I mean, it's not fun, and it's really not technological at its core, is what we do today in surgery. And what's more, it hasn't really changed for the past 100 years. This is an OR 100 years ago, and really the only advancement for most surgery, I won't say all surgery, but most surgery, is the antiseptic techniques, where we now have sterilization, and so we have less infection. So that's changed. But fundamentally, what these guys are doing and what these guys are doing is very much the same. I've got to warn you, the next slide, it's a medical robotics talk. There's going to be some blood and guts. Okay, so I don't have much of it in my talk, but the next slide, just to drive home the point of what surgery is like today, has blood and guts. So if you're sensitive to that, just close your eyes for a minute. We'll get past it quick, but I want to warn everybody. Okay. So here it comes. This is what surgery looks like today. So this is a person's abdomen cut open. These are intestines, and these are doctors' hands. And what are they doing? They're digging around inside the patient to try and find the structures they want to find, the problem, the tumor, whatever it might be. And really, I mean, it's nothing more or less than slicing someone open and putting your hands inside and digging around. So I'll go past that quickly. But that's what surgery is. That's what it is today. That's what it was 100 years ago. So if you have any myth in your head about how technologically wonderful it is, we're starting to get some technology in there, but by and large, surgery does not have much technology involved. So here's an example of another issue that we have in surgery. This happens all the time. This is a doctor who's trying to biopsy something, and it's maybe a liver tumor. This is a patient's abdomen. This is an ultrasound machine. So the doctor's waving this ultrasound machine across the patient's surface, getting an image up here, and then with his other hand, he's taking a needle and he's trying to coordinate what he's seeing there with what's down here and with where he's imaging, and with hand-eye coordination, hit that tumor with the tip of the needle. So you can picture yourself doing this. It's a very imprecise process, and this begs for machines. I mean, this is a registration problem, is what we call it. It's where you're matching one imaging space, this world of images, to the physical patient, and then trying to get a physical thing to a point in that space. And so that's something machines can do really well, and people can't. Yet still, this is how we do it. Here's another example. This is a knee surgery. So if you've ever had or known someone who got a knee implant of any kind. This is what they do, and this is a power tool. I mean, it's like what you or I might do in our garage with a piece of wood. I mean, the doctor holds the drill up and aims it by hand-eye coordination and drills a hole, puts in a screw. It's very much like carpentry, and this is what goes on in our ORs today. Okay, enough of what's wrong with it. Let's think about what it could be. Okay, this is Russ Taylor. He's the director of Engineering Research Center for Computer Integrated Surgery at Johns Hopkins, which is where I did my Ph.D. about 5 years ago. And what he said is that the impact of computer integrated surgical systems, and this includes robots and anything you do with a computer in surgery, in the next 20 years will be as great as the impact in the last 20 years of robots in manufacturing has been. What you see down here, these are Toyota Camrys being made. And just think about what this process was like when we had the Model T, right? It was a lot of people assembling things by hand. And now we've got these huge teams of robots that are moving in a coordinated fashion. We've got the assembly line coming through, and they're welding these different things onto the car. But you can see the impact that this technological, computer integrated manufacturing has had on the things that we have, our cars. So if he's correct that we're going to have the same impact in medicine in the next 20 years, which I think he is, we're in for a big change in how surgery is done. And that's what I want to talk about today. So here's a little science fiction of what it might be in the future. This is a scene from Terra Nova, which was a series that only lasted 1 year. It just finished. And here she's doing surgery on it's actually a dinosaur egg, so they went back to the past, and she's fixing this dinosaur that's inside of its egg. But what this illustrates is the potential and what could be surgery in a few years from now. So what you see here, you see really wonderful three-dimensional images that include blood vessels, include all kinds of structures. She can slice them, she can rotate them whatever way she wants. She's got voice control. She can tell this imaging thing what to do. She can move stuff around with these little pointers that she's got. And back here's a robot, and this robot is inside the dinosaur egg through these little ports, and it's moving around, and it's actually doing the surgery that she's commanding it to do. So this is a glimpse of what the future might be. So let's see how close we are right now to making this stuff a reality. Okay, so this is a slide one of my doctor friends put together. This is what he wants. He wants me to give him, as an engineer, to give him superpowers. And he defines superpowers as amazing X-ray vision, being able to see the margin of the tumors that he wants to hit, and also having some kind of hand that's much smaller than his that he can reach in to the patient and do that surgery with. And so you can see that that's pretty similar. I mean, he really wants this system that they're using in Terra Nova. That's what he wants. And he considers that superpower. So that's what we engineers are trying to give him. So how close are we to that? Well, this slide shows a system that is the product of a startup company that came out of Vanderbilt University. It's a local Nashville company. And their product, what they do is they help the doctor find his way in surgery. So it's surgical GPS. Just like in your car, your GPS system tells you where you are. This is the GPS system for surgeons. And what it's telling the doctor is this green thing is the surgical tool. This is the instrument here that he's cutting with. And it's showing him where that is with respect to the yellow is the plane of resection. He wants to cut on that yellow plane and not anywhere else. And what's more, it's showing him where the tumor is. And it's showing him where all these major blood vessels and bile ducts are that he doesn't want to cut. Because if he cuts a little bit too far this way, he cuts a lot of major vessels and he has bleeding all over the place. And if he cuts a little bit too far that way, he's going to leave some tumor behind, and the whole point of the surgery won't be accomplished. So what this does, it gives him GPS and it lets him see where his tool is in real time. So it's a heads-up display. It's shown on a monitor above the patient. And lets the doctor know where he's going. So that's pretty similar to that hologram. It's not a hologram yet, it's on a screen, but it's showing the doctor where he is. And this, like I said, it was spun out of Vanderbilt Research. These are a couple guys in biomedical engineering, urology, and they've developed this system. It's now deployed in, I think, 5 or 6 hospitals across the country, and they've got more orders, and they're trying to get the system out there to a broader audience. So it's really a new thing that's just getting there.
Question.
Yeah. That is a great question. The answer is no, it is not. And the reason is that we have not found the liver surgeons here at Vanderbilt who were wanting to adopt this technology. It takes sort of a unique surgeon to be the first adopter of a new technology, because it's a little bit of a risk, right? It's a little bit of a risk for them because, I mean, they're responsible for the patient's life at the end of the day. If something goes wrong, they're liable at the end of the day. So they have to step out on a limb a little bit, and they have to work with the engineers to be comfortable enough with the technology that they can do that. Only certain doctors are willing. So the old school guys who just have done it the same way 1,000 times and want to do it the same way the 1,001st time, they're not going to use this stuff until it gets out there enough. And then there's this marketing push because everybody else is using it. Why aren't you? I'm going to go across the street and have my liver surgery done because they have the latest technology and you don't. And then they'll get dragged along with the flow. But it takes a little while before you get those guys into using it. So we're actually, with this system, we're working with some doctors in New York at Memorial Sloan Kettering as first adopters. They're our closest point of contact. And this guy's actually a urologist, so we're now starting to use it in kidney surgery as opposed to liver surgery. But the company's product is liver surgery. So there's a little bit of, distinction there between medical specialties and trying to get different doctors to use it. So great question, though. Unfortunately, I wish I could say we were using it right there, but no. Okay, so as far as robotics, as far as the little hands that were inside that dinosaur egg, where are we? Well, this is what I would call the Model T of robots. And it's called the Da Vinci Surgical System. Many of you may have heard of it. If you've ever heard of anything of surgical robotics, it's most likely this robot that you've heard of. What it does, the doctor sits here at a console. This is a picture of what the doctor's hands are doing. And these are the robot's hands, which are inside the patient. The patient's on the bed. The robot has the hands inside. And as the doctor moves his hands around, these instrument tips move in the same way. And it's really immersive because the doctor here is seeing this image and it's superimposed on where his hands are. So he feels like the robot hands are his hands. And it's really easy to just sit down at this console and do a complicated surgery. It's great. I've tried it. If you ever have a chance to try one, go for it. It's really fun. But this is the Model T of robots. It's the first robot that's gotten out there. It's built by hand on an assembly line. There's a lot of parallels to the Model T. So it's basically, think what our cars are today versus what the Model T was. This is what robots are today. They're at the Model T stage. They need to get a lot better. So at Vanderbilt, we have a unique opportunity in this field, which is just at the point where it's about to go widespread. The next, like Russ Taylor said, the next 20 years are going to be amazing in medical robotics. We have a unique opportunity because the medical center is right there, and we have a world-class engineering school, and they're on the same campus. There's very few places that can say that. And what's more, we have engineers who do this kind of work. So everybody here in a gray box is an engineer, and everybody here in a red box is a doctor. So you can tell we have a pretty big team of people on both sides, both the medical school and engineering, and lots of existing collaborations. And what Vanderbilt realized about a year ago, as we communicated this to them, was that there's a big opportunity for the university to support this and create what we call VICE, which is the Vanderbilt Initiative in Surgery and Engineering. And it includes all these disciplines in the medical center side and all these disciplines on the engineering side. We've got about $20 million in research already, just pooling the research that we have, and about 20 different faculty members. So this is a brand new thing, just happened within the last year here at Vanderbilt, and we're going to really lead the charge in this area. Okay, so what is this area? What can robots do in the future in surgery? Can they only operate on dinosaur eggs? Can they only do what the Da Vinci does? Well, no. This is sort of an outline slide of the rest of my talk. I'm going to tell you about the different things they can do. So it really boils down to several key advantages that robots can have. They can drill, cut, shape, or manipulate bone. So this is a piece of bone the robot's drilling. That's one thing they can do. The other thing they can do is hit a target a lot better than we can as humans. That's what the doctor was doing with the ultrasound probe, trying to hit a target with a needle. Robots can do that a lot better. They can become tiny and start moving around inside the body to do different surgical jobs. And I'll get to what jobs those are in a minute, but we can have tiny mobile robots that move around in surgery. And lastly, they can reach dexterously into small spaces. So there can be a lot of future iterations on this concept with better tools that will get us into smaller spaces in the body. So let's first talk about the bone shaping. So this is where surgical robots got its start. And this is the very first surgical robot, which is really just an industrial robot that was used in car manufacturing, that somebody at a university took into their lab and said, we're going to have this thing aim a needle into the brain. So that was the first thing a robot did. It's 1985 is when this paper was published. And the robot held a needle guide, and then the surgeon could push a needle into the brain and hit a target. That's what this guy did. I wish I had a better picture, but that's the best you can get from a paper from 1985. So this led to the first two companies. This is the Robotic system, and this is the Neuromate system. And these two came in parallel. They started in the early 90s, and they were the first two medical robotic companies. This one did knee and hip implants, and this one aimed needles into the brain. So this is a video of what the modern knee and hip implant robot looks like. This is the Mako surgical system. If any of you have seen billboards up advertising robot knee surgery, this is the robot that they're talking about. So I'll play this video. This is how it works. The doctor holds on to the drill, and the robot is also holding the drill. And so as the doctor moves, the robot has this 3D model inside of it, inside the computer system, of the bone and the exact volume that the doctor wants to cut out with that drill. And the robot prevents the doctor from going too deep. So the doctor is still doing the drilling, but if he tries to push way into that bone, the robot will stop him. So it enforces safety zones and makes sure that the shaping is correct on that implant. So here at Vanderbilt, we're pushing this sort of to the next level, which is, okay, knees you can be off by a little bit, and the implant might still work. Well, this is right behind the ear. This is what the doctor's drilling out, and this is a doctor doing it by hand. This is a robot doing it. And this is the first step in almost any kind of inner ear surgery that you would have, is this procedure. It's called a mastoidectomy, and it's the knob of bone that you can feel with your finger right behind your ear. It's removing that. It's cutting that away so that you can get into the inner ear structures. Okay? The tough thing about this is that inside of that bone are nerves. So the nerve that goes to your face and controls all of the motion in your face runs right through there. And the nerve that goes to your tongue that controls all of your taste goes right through there as well. And if the doctor accidentally cuts one of those, then you won't be able to move your face or taste again. And what's worse is that nerve is right here. And you can see how close the doctor had to get. It's within 0.5 millimeter of that nerve. And so one slip of the hand and that nerve can be cut, and that's a really bad consequence for the patient. So we would love to have robots that can do this very accurately and precisely. Just like in the manufacturing world, we've gone from humans doing stuff, which had high failure rates, to machines doing stuff, which have much lower failure rates. So we're trying to do that with robots in inner ear surgery. And that robot I just showed is set up over at the medical center, and my students and I use it all the time. This is another robot system that's on the commercial market that was just FDA approved a couple of years ago. This one is for spine surgery. So this robot, you'll see more pictures of it, but what it's doing is guiding a drill into the spine. So when you have to have spinal fusion, you have to put a bunch of screws into the spine, connect them with metal rods, and then that stabilizes it if you've broken your spine. So this is what the console looks like. And you're going to see the planning process. So it starts with the planning stage, where the doctor's looking at the spine, looking at what's broken in the vertebrae, looking at which ones does he need to fuse together. So he has this nice interface where he can look at the images. The CD is unimportant, but gets us to the next step. So you take a high-resolution scan, and you have a 3D model, just like we had with the knee implant. And then what will happen is the doctor will put screws into that. So in the virtual, inside the image, the doctor can play around with, I want the screws to be this size, I want them to be at this angle so they don't hit the spinal cord, and I want to have the rods that connect them have this geometry. So he can play around with that, he can get it just right. So what they do today without this robot system is they do it all by hand and by eye. They take a drill and they hold it up there and they just try and get the hole in the right spot. So what they do with the robot, what he's doing right now is he's attaching these things so that he can put the robot onto the person's spine. So you put these pegs into the hip bones, and then you put this T-frame on, and that holds the robot. And this is the robot. They put it through a bag so that it can be sterile. And they attach it on eventually to this T-frame, lock it in place. And now there's going to be an arm that comes off the side that holds a guide. So this is a guide here. And the hole that's supposed to be drilled goes right down into the spine there. So they can put the drill straight down. This guide tube goes right up to the spine. And they can now put the drill through that guide into the bone. They sort of hammer it in a little bit. And they put the drill down, drill the hole, and you can see the screw is going in exactly the right place. So I would much rather have a machine lining that up than a doctor using hand-eye coordination and trying to drill the hole in the right spot. So that's the Mazor robot. We're taking that same concept, and again, we're pushing it to harder clinical cases, which are, again, in inner ear surgery. So this is a cochlear implant system. So if you're deaf, you will need to get one of these to be able to hear again. It can restore hearing to anybody, almost anybody who's deaf, because normally the cause of deafness is the cells inside the cochlea die. And so what happens is you insert this electrode array, and it stimulates electrically those same nerves that would have normally been stimulated by the hair cells. So if you input this electrode array, and then you have this external microphone that talks to it, you can stimulate those cells, and you can return hearing to somebody who's deaf. So we're trying to build a robot that will help with that, so that the doctor doesn't have to, again, drill by hand very close to these nerves. And this is what the robot looks like. It's a parallel platform robot with legs that move up and down and tilt. And we can couple on a drill to this and drill very precisely down into the head. The drill you can see here, this is a cadaver bone. And for scale, this is a Coke can. So it's a very small robot that would be attached to the head right behind the ear. This is what it looks like with the drill on it. So we've got a drill press here that has a stop, so you go just the right depth. And this is a CT scan of the drill. So this is the drill. This is the cochlea. And you can see that we've hit exactly the right spot. And the nerves are somewhere like right here, up in that area. So we've managed to miss the nerves and hit the right spot in the cochlea. Then once we get there, we have a problem. So we've got to insert the electrode array. This is the electrode array. And the way it works is it's a silicone thing. It's very soft, rubbery stuff. And it's curved into a circular shape. And so to get it to deploy into the cochlea, you have to pull out this stylet, which is a piece of metal wire. So you pull that out, and it returns to its curved shape. And this is a picture of what it looks like going in. You can see the tip of that thing curving around the corner. This is a model of the cochlea. And so we built this robot that controls both the electrode array itself and the stylet. The doctors do it right now this way with tweezers. So they have that opening that they drilled, and then they reach in with tweezers, and they extend the electrode array. And we have now a robot that can do that same job through a tiny little hole. So rather than having to make this big opening, we make a single drill shot, and we go in. OK, so that's it for the bone section of the talk. Next, I want to talk about how you hit targets with these robots better than humans can. And so this is a picture of doing a needle placement. So this is exactly what we saw with the doctor doing the ultrasound probe and then trying to hit a target with a needle. We can do that a lot better. And we can do it. This is a CT scanner. And this is a robot that goes inside the CT scanner. And the robot then, when you're in the scanner, can take a needle and put it exactly to the spot you want in the image. This is the image. And so here's the target. So what the doctors interface with this system, what he would do is he'd go up and he'd say, well, that's the problem right there. And he'd click on that spot on the screen. And then he'd say, well, I want you to insert right there. And he'd click on that spot on the screen. And then the robot does the rest. So you have the scanner there. The robot aligns itself. It uses this rotational degrees of freedom here, lines itself up with the target, and then you insert and you hit the target exactly. So this is a big step up from doing it by hand. And it comes from the fact that you know where your robot is with respect to the image. You do it all one-stop shopping in the scanner rather than having the doctor look at a bunch of images and then try and do it over here by hand-eye coordination. So that's a big step forward. Unfortunately, that system is not commercialized. This one is. They tried. They tried with GE. They failed. It was mostly due to business issues, not technical issues, but hopefully it will get commercialized at some point in the future. This one is, though, and this is one of the coolest robotic systems out there right now because there's two robots involved. We've got one robot holding the patient. I don't know if you noticed, but at the very beginning of the video, here you can see it tilt a little bit. This robot can actually adjust the bed while this robot aims a big X-ray cannon at the patient. And what you're doing here is radiosurgery. So it's sending X-rays into a tumor, and you want to send them from a whole bunch of different directions because you don't want to kill the tissue on the way to the tumor. So you can't just hold it in one place and blast away, or you'd bore a hole through the patient. So what you do is you aim it from a whole bunch of different directions, and you do multiple shots, and where they triangulate is the tumor, and that tissue dies, and the rest of the tissue doesn't. And the only way that that's possible is by taking this big X-ray machine on the end of this huge, enormous robot and waving around that X-ray source, and then also adjusting the patient at the same time. So this is really like an industrial robot, like the ones you saw working on the cars. This is the same kind of robot, only it's working on a patient now, and there's 2 robots cooperating. That system, by the way, is commercialized. It's in about 100 different hospitals all around the world. It's being used widely for all kinds of things: lung surgery, brain surgery, prostate, lots of things. Almost any kind of cancer you could name, they've probably tried it. Okay, so that's it for the second part, a little bit shorter, but on the aligning and aiming thing that robots can do. It's a cyber knife. Yep, cyber knife. So this is 8x speed, by the way. The robot doesn't actually move this fast. It would be scary to have a robot waving around you at that speed. You can see his breathing. That gives you he's not really panting. He's closing his eyes, hopefully trying to just relax and not think about the fact that there's a monstrous robot waving an X-ray gun around him. That's prostate. That's prostate. But if you go on YouTube and you type in cyberknife, you can find lung and you can find brain and you can find all kinds of other, probably all the soft tissues in the abdomen as well. And it's really the same system. The only difference is if they do lung, what they have to do is put some markers on the chest, and then this is a camera system that watches those as they go up and down, and then the robot will actually adjust for that. So as the person breathes and the tumor moves, the robot will move itself to track where that tumor is going. So, but in prostate, you don't have to do that because there's not as much motion of the prostate with respiration. Okay, so another thing robots can do is run around inside the human body. So this is something that science fiction has anticipated a long time ago, Asimov, Fantastic Voyage, and more recently with the bug that went into Neo in the Matrix. You guys remember the thing that crawled into his belly button? I wish we had something as good as that and we could put it to good medical uses. We aren't quite there yet, but this is a big step in that direction. And this is a robot that I built a couple of years ago with these guys in Italy. Actually, I didn't work on that one. I worked on the revision after that had a few more legs on it. But I'll tell you about the big picture of this is these pill cams. Some of you may have heard of these or known people who've swallowed these pill cams. What they are, it's a camera inside of a pill that you swallow. It goes through, there's electrodes on the surface of the body that capture the images. It's an antenna, and it transmits them out. So this guy is snapping images all through the intestines as it passes through, sending them outside the body. So you get the great thing about this is small intestine, because the small intestine is so hard to see without this, because it's way in there, and it's around lots of corners, so you can't really get an endoscope down the throat far enough or up the other direction far enough to see in the small intestine. So these things they've sold well over 1 million of these, and they've been using them clinically for about 10 years, and they're really the gold standard for how you look at the small intestine right now. So that's where the commercial world is, and where we're going is robots that can do more than that. So we don't want to just see the problem. We want to actually get in there with the robot and treat it right at the same time as we see it. Because the big problem with seeing it is you don't know where it is. So then you're back to that gory image I showed at the beginning of the talk with the doctor rooting around inside there trying to figure out what intestine he saw the picture that he saw with the camera in. So the first step for us, then this was a number of years ago, was to put legs on the capsule. And that lets the capsule control its position. And we made wireless versions of this that you could swallow. And it would let the bug walk around inside the intestines. This is a fluoroscope image of it crawling through the intestine. And it can stop itself. It can look really closely at areas where you think you might have problems. So this was a nice step forward. But the only way that we can really do something super useful with, just an aside, it's really hard to make these. It's like being a watchmaker. So there's 72 tiny little parts. You can see a human finger for scale. We have a couple tiny motors. So we had to work really hard manufacturing all these tiny little parts, but these are all what go into that robot that you saw. But to make these things really useful, what we've got to do is endow them with the interventional capability, so some ability to treat what they find. So this is the first one that was able to treat anything, and that was about 2009, so very recently. And what this robot did, it had a one-shot clip on the front. So if you found a spot where it was bleeding, you could push the robot up against that spot and deploy the clip, and it would stop the bleeding. And that's usually what you're seeing in the small intestine is bleeding. So another very cool cutting-edge idea in this mobile medical robot world is magnetic control of robots. So this is a tiny little micro blimp, football-shaped object. and it's swimming around inside the eyeball. So that's what you saw at the beginning, was it injecting it into an eyeball. And there's a huge series of electromagnets around it. So this is where the human head would go. And so you have to put your head, yeah, you got to put your head in this big contraption. But what that lets you do is it lets you have strong enough magnetic fields that you can make this thing go where you want. And so they're showing here spinning it around, swimming it around. And this is super useful if you want to treat, say, glaucoma or other diseases of the retina where you've got to go in and inject something at the retina. Particularly if you have blood clots in the retina, that's what their first application was, is blood clots. So you go in, and this is a chick embryo which really well replicates the back of the eyeball. And there's blood vessels that are just like what are on the retina. And so this is showing pushing a needle into those tiny little blood vessels with magnetic fields. And then they inject a little bit of declotting agent, which causes that to break up the clot. So very cool, very recent new stuff. Here's another cool robot that crawls around inside the body. This is the heart. This is a pig heart. This robot uses suction cups. So what it's doing, it's crawling on the heart. And you wouldn't do it this way for real. You wouldn't like open up the chest, because if you did this, you could just inject whatever you want to inject. You know, you take a needle and stick it in. But if you're doing this in the closed chest, then you could insert this robot through a very tiny hole and have it crawl around on the heart and crawl to the back side of the heart and inject some stem cells, for example, which would treat a heart attack, or any other agent that could treat diseased heart tissue. And this shows basically what this was showing is it walking around. I think, yeah, this video plays too. So this is without cutting the membrane that's over top of the heart. It's actually crawling under that membrane and on the surface of the heart, showing that it can make headway using these suction cups and this inchworm technique to get around on the heart. Okay, so lots of cool ideas being explored in this space, this mobile space. Almost none of them, I think I can say none of them yet used in humans that I am aware of. So these are all research lab kind of things, and they will get there, but it'll take a few years. Okay, so last thing that I want to talk about is how can we make these Model T robots better and make them really useful in areas like, say, in the head, where you have small spaces, down the throat, in the nose, anywhere in the body where you don't have a big abdomen that you can inflate and create all this space, which is what this robot requires. So here, this is another cardiac application. This is a company that manufactures this catheter. And what it does is it goes inside the heart. So you go up through the blood vessels. And you go inside the heart, and it has a little electrocautery tip. And what it will do is it'll actually burn the inside wall of the heart. And what that does is stops unwanted electrical activity from happening. So a lot of times if you have fibrillation, which is where the heart just sort of flutters uncontrollably, the reason is you have some bad electrical connections. So if you can go in and cut those wires, it helps the heart beat in the correct pattern. And so that's what this robot is all about. It's got this controllable, bendable tip on it, and it can go in the heart and cauterize that inside wall. So that's a big step forward in terms of smallness and dexterity compared to the Model T robot that I showed. What we're doing in my lab, one of the main projects in my lab in the mechanical engineering department are these robots, which are actually a big step forward in terms of size reduction. So this is the size of a needle. The last one I showed you, it was about 4 or 5 millimeters. So it was about, about the size of maybe a pencil diameter. This one is down to needle diameter. So we've gone way small. And the way we do it and still get this tentacle-like undulation and ability to deploy in complex trajectories is we have several tubes. So these robots are like, think about a TV antenna, one of the old style ones that would telescope out. It was a bunch of concentric tubes. Now think about each one of those tubes being flexible and curved. So what happens if you stuff a whole bunch of those inside of each other, and then you grab each one at the back end and you rotate it and you slide it in and out? Well, the result is this sort of tentacle-like motion with a robot that's the size of a needle. And that's what's being shown here. This is the same kind of robot. We've got a little gripper on the end, and we're showing that we can deploy to different locations and just generally how it moves in that video. So why do we want to create robots like this? Well, one of the applications we're going really hard after right now is endonasal surgery. So when you have tumors in the very center of your head, it's a big problem because there's no way to get there. So a tumor here, I mean, what do? If If you go in from the top, you got all this brain you got to get through. You go in from the side, same deal. So the path that you'd love to take is in through the nose. But it's really hard to do that because the doctors are trying to coordinate lots of tools in a tiny space, and the tools are running into each other, and they just can't do it in most patients. Plus, there's carotid arteries are running through here, optic nerves are running through here. There's a lot of really bad stuff to hit here. So they still do it open, and I'll spare you the gory pictures, but the open procedures involve cutting through the forehead and going in through here, or going in with a big hole in the cheek. They're horrible, horrible pictures. I'm not going to show them to you, but trust me, they're bad. Okay, so a lot of people, actually 1 in 5 of us will have a pituitary tumor in our life. So it's hard to believe it's that high incidence. The nice thing about these tumors is they grow really slow. So for a lot of us, we'll die of other causes before the pituitary tumor gets us, which may or may not be comforting to you. But a lot of us will have them. And as lifespans get longer, it's going to be more and more of a problem of we're going to have ways to treat these because more and more people will need them treated. And a lot of people do need them treated today. And actually, in addition to that, so that's just the ones in this green area. The ones in the orange area account for about 49 or 39% of all brain tumors are right in this area. And we would love to be able to go up here and turn a corner and get to these through the nose as well. So this is what we envision. This is just like the same concept as that Model T robot, the intuitive surgical robot, where we have a robot here that goes up the patient's nose, and we have a doctor sitting at this nice console with lots of visual overlays and enhancement and image data and all kinds of information at his fingertips so he can see how best to treat this problem inside the patient. Here's what the system we have in the lab right now. This is set up over in Olin Hall right now. This is our robot. This is a head model. This is me actually sitting at our console controlling the robot. And here you see how the robot moves. So these are the little robot hands up here. It's kind of hard to see them because they're so small. It's just hard to take pictures of things that are the size of a needle. But you can see that this would be the doctor's hands moving these around, and you can see how the robot hands mimic the motions that the doctor is making. So that's our system. We've tried it. We've used it in a cadaver. This was an experiment over in the Vanderbilt Hospital on a cadaver head. So we put it up there, and we tried to see if we could actually work around in the pituitary area. And this is a picture of the robot hands reaching that point. And here's some of the latest results. The nice thing about these robots is since they're flexible, we can actually use the robot to sense forces. So this is really important for doctors because they feel everything. You saw those hands in the abdomen. They're feeling everything all the time. And with these robots, if we can tell where they are, we know that they're flexible, and so we can use the deformation of the robot to actually extract the forces that must have been applied to it, and then give those forces back to the doctor at the doctor's controls. And also we're designing this new robot that has lots and lots of motors, 4 different arms. They'll all go up a single nostril. So these are latest results just out of the lab. The last thing on that same robot topic, this is the last surgical topic I'm going to talk about, same robot, is lung surgery. We can use these same curved needle diameter robots to get down deep into the lung. And this is an enormous problem because if you have to have lung surgery, you're going to have a scar like this. It's very traumatic. The chest has to be cracked open. It's just horrible. And so what happens is a lot of times a person will get a chest scan, and the doctor will look at it and be like, I don't know if there's cancer here. You've got this spot here. It kind of looks funny. We can't tell anything. Go home, come back in 3 months. We'll scan it again. And so this patient has to walk around for 3 months not knowing whether they have cancer, and knowing at the same time that if they do, their odds of their 5-year survival rate is like in the single digits. Their 1-year survival rate is like 10%. So you're pretty much going to die if you have it. And you know it's getting worse every day because it's growing. And yet we can't do anything about it because we can't reach it. And if we did, we'd have to cut somebody open like this. So it's this horrible catch-22 situation. And the doctor with current scopes can only reach about 1/3 of the lung. So if the tumor's not in that area, you can't biopsy it. You can't get to it. So what we're going to do is we're going to deploy those little needle-sized robots out the end of this and reach that peripheral lung area through the throat path. And here's a picture of how we're going to do that. We've got these wonderful images. We can plan the shapes we need to get to the target. We can make it custom for each patient. So we can look at a scan of that patient, and we can know where the tumor is, and then we can make the needle just right so that it's going to get there. Then we can deploy it through the bronchoscope so it comes out. This is a standard clinical bronchoscope. So it comes out, and then put a little gripper on the end, and it can reach out here to the peripheral lung and grab a biopsy sample. And we're also doing, this is a motion planning work where we're trying to hit a specific target in that image data set with this robot. So this is, we're just starting to work on this, but I think it could have a huge impact on how we treat these patients who have suspected lung cancer. Okay, so now you know. This is what robots can do in surgery. They can drill, cut, and shape bone. They can reach into small spaces dexterously and help the doctors have smaller hands. They can aim things, needles or X-ray beams, more accurately. And they can also be mobile and treat things as they walk around through the body, particularly in the GI tract. And I want to leave you with a couple take-home thoughts before we take questions. So I don't know if any of you have seen this little cartoon before. I don't think we'll ever get to the point where you're buying your robot surgery out of a vending machine. However, we do have machines doing parts of it now, so in the far distant future, maybe that'll be the same day we have the Terminator surgery. But I don't think we'll ever get to that point. But we can certainly do better than this. We have already today have the technology to do a lot better than this. We just have to put it all together and get it in doctors' hands and get them to adopt it. And put these different pieces of technology that I showed you together. We actually have a lot of the pieces and parts we need to make a system like this. It's just a matter of doing the work. It's hard work. It's hard research to build better robots, to build better interfaces for the doctors, and to give the doctors the information they need in real time to do the surgery that they're trying to do. So it's coming. Russ Taylor is completely right. In the next 20 years, we're going to see a revolution in how surgery is done, and most surgeries will have some form of automation involved in them and some form of mechanical assistance from robots. So thank you all for your attention.